Well, we're beginning to talk about vectors in this section. And as you can read, vectors are entities that have both direction and magnitude. And force is a good example of a vector. When you apply a force, or when a force is applied, it's a force applied at a certain amount of force, and it's applied in a particular direction. So force has a magnitude, like 10 pounds of force, in a particular direction. Velocity as opposed to speed. Speed is exactly that. Velocity, the magnitude of velocity is speed, and it's speed in a particular direction. So velocity includes the idea of direction. And in this section, made up of several videos probably, we're going to look at vectors both represented geometrically and algebraically. First, we start out with the geometric representation, though. So to get the idea of direction, we have what are called directed line segments. And in a directed line segment, as we'll see in a moment, the length of the line segment represents the magnitude of the vector, the directed line segment. And of course, direction, we have some idea because we can see how it's pointing, where it starts and where it stops, and that gives us some idea of direction, the pointing of it. So the directed line segment below, that is the directed line segment starting at point P and going to point Q, and that's the reason it's written in this way. Starts at P, goes to Q. Those are 2 points in the plane. So it has this initial point, is what we call it, P, and a terminal point which stops Q, and its magnitude or length is denoted by double absolute value bars here, and can be found by using the distance formula, which we're not too concerned about that yet. We'll see that a little later. So here's an example of a directed line segment. See, we're starting at P, and so we just have a solid dot there. We're going to Q, we have a solid dot there, but the end of this line segment, you see a little arrowhead, and so that's telling us where we start and where we end, and that's why it's called directed. Now, vectors can be written in several ways, and it's rare that we use this notation, directed line segment from P to Q. We'll see later on that we just represent this vector by a vector name, and vector names are usually V's and U's. And in your book, or in my math lab or some other software, vectors are usually lowercase bold letters, but since I really can't make my letters bold by writing them, a lot of times we put a little arrowhead on top to indicate that we're talking about a vector. Now remember, the only thing that's important about a vector is its magnitude, that's the length in this case, and its direction. So we could have, see, all of these directed line segments are the same length and they're in the same direction because they're parallel. Those all represent the same vector. So where a vector is in the plane makes no difference. Where it is makes no difference. It's its length, the magnitude, and its direction, the angle at which it's moving. And the point here is these are all examples of the same vector. They're all equivalent directed line segments. And here's just a simple, this is basically a restatement of what I've already said, and adding one little bit of information, again, just having written it. Notice here we have a directed line segment from P to Q, and so that's representing this vector. But as I said before, in type, in print, we would see that lowercase v rather than with a little arrow on top of it. In this case, v is representing this vector. But we could start at a different point and end at a different point, but as long as we were parallel and exactly the same length, then these would be equivalent vectors. See, let's look over here from P to Q. Let's look at this, the horizontal displacement change. Here's 1, 2, 3, 4 units it changes horizontally, and 1, 2, 3 units it changes vertically. So here, 1, 2, 3, 4 horizontally, 1, 2, 3 vertically. exactly the same length, the same way it moves. Here, 1, 2, 3, 4 horizontally, 1, 2, 3 vertically. So they look the same length, and in fact they are. And also we see that they're same direction. So all three of these vectors are equal, if you will. They represent the same vector. They're just in a different position. Well, next we're going to be talking about some operations on vectors and things that we do to vectors. We have what's called scalar multiplication. We have addition and subtraction of vectors. And at a later time, we'll have something called the dot product, multiplying two vectors. And on the next page, we begin this discussion, and it starts with scalar multiplication. So let's kind of digest this a little bit at a time. Let's first look up here at this paragraph, and what it says, of course, is scalar multiplication refers to multiplying a vector by a number. That number is the scalar. A scalar is a real number, and we call it a scalar when it's used in conjunction with something that's not a real number, like a vector. If the number is positive, as you'll see below, if the number is positive, the multiplication changes only the magnitude of the vector. That is, it makes it longer or shorter. It doesn't change the direction. If the scalar is negative, it results in a vector in the opposite direction. So the idea and the reason it's called a scalar is it scales the vector. It scales it up or scales it down. It makes it twice as long or 1/2 as long, as an example. So just to illustrate the idea here, I've got a vector v. Okay, this first vector is vector v. And I've got this, the way I've written it here, it helps us identify. Well, if we take the vector v and multiply it by 1/2, that would be the scalar 1/2. We'll multiply it by 1/2. All it's going to do is give us a vector that's in the same direction but half as long. It has half the magnitude. So this is half of v, 1/2 times v. On the other hand, if we take the vector v and multiply it by the scalar 2, or 2, we're going to get a vector that's twice as long. And so you see here, this 2v, exactly the same direction. All it's done is scaled v up by a factor of 2, by a magnitude of 2. It's made it twice as long. Now, if we multiply v by a -1, or we normally just call it a negative v, well, all that does is it doesn't change, in this case, the magnitude, but it makes v, the opposite of v, or negative v, is a vector that is exactly the opposite direction of v. And then in the last case, you see -3/2 times v. Well, what that does, the negative makes the vector go in the opposite direction of v, and the 3/2, which is the same as 1/2, makes the vector 1.5 times as long as the original vector, but of course in the opposite direction. Well, on the next page, the next view, we're going to talk about the addition and subtraction of vectors. Now, we're talking about geometrically, okay? And what we find out in this section is it's nice to know the idea of the geometric representation of these vectors, but when we get into something that's significant in dealing with vectors, it becomes very clumsy to pull line segments out, directed line segments, and try to move them around. But that's it. It gets us started, and that's what we're doing now. So we're going to talk about addition and subtraction. So let's just consider, look over here at the left side, not the right side. We've got a vector u and we've got a vector v, and they're just in the plane anywhere. And remember, if I could pick these up, and I'm not able to here, let me draw a little example though. And I apologize for, okay. So here, oops, that didn't work very well. Well, that's not what I wanted to do. And I've really messed this up, haven't I? I apologize for that. But let's take, okay, let's look at the one. You're seeing me struggle a little bit here. Okay, so here we've got a vector just as a point. Here we've got a vector, and I'm sorry. I have to laugh at myself. Here we've got this vector, and it's the same vector no matter where we put it. See, I mean, that vector is the same. It's exactly the same direction. This is what I should have done to begin with. Okay, and that vector is the same no matter where we put it. And if we want to add two vectors together, then we start with one of them and we put the other one at the ending of the first. And that kind of gives us a beginning position and in total an ending position. And we could have put it either with either one of these. Well, that's what I'm trying to illustrate here. Okay, so we've got this vector u and v. Let's go back to my original. And vector u happens to be sitting right here. Okay, sitting right here. And we want to add u and v together. So what we'll do is we'll act like we can pick up v and move it to the position where the beginning of v starts at the ending of u. Okay, and then the new vector, adding those two together, you see over here, it would be from the very beginning to the very end. So here is my original u. Here is my v moved to this position. U plus v starts at the beginning of u and stops at the ending of v. So this dark vector right here is u plus v. Okay, and that's not really too hard to do. Sometimes it's a little, like I said, a little clunky when because we can't really pick those up very well. Now, the next thing that we kind of have to imagine, don't we? The next thing we want to do, that's addition, okay? Next thing we want to do is subtract two vectors. We have a vector, just the same two vectors we've got up here, u and v, for instance, and we want to subtract v from u minus v. Well, to do that, we think of writing it as u plus the opposite of v. That, you know, that's really what subtraction is. It's adding the negative. And so what we're going to do, let's look at this diagram. See, here, and by the way, here's what I've really done. Here's what I've really done. Let's imagine what we most like to do is have vectors, if we can, start at the origin. And so what I've done in the illustration below, I've taken this u and I've put its beginning point at the origin. Remember, it's the same vector no matter where it starts. It's going to be the same length and the same direction, so it doesn't really matter. So I've taken that vector u, just imagine, and I've got a little different scale, but I put it right here. And I've got a vector v, and in fact we can just use these. I've got a vector u and a vector v. I just conveniently had them both start at the origin. So if I want to look at u minus v, here's what I do, okay? Here's u. Now, the negative of v, see, here's v right here. The negative of v would actually be a vector that starts here and goes in this direction, okay? Here's v, negative v would start and end just oppositely. So starting here and ending here. Now what I'm doing is I'm actually putting that negative v vector up here. So you can see that this vector, negative v, would be the same as if I had it down here. Okay, so here's my u, and I'm adding negative v. That's the same thing as u minus v. Here's my u, and I'm adding negative v. Now, so here's the very beginning. Here's the very ending. And so u plus negative v is this vector right here, u minus v. This is u minus v. Now, it's the same vector if I would have put it clear out here. See, this is the same vector way out here. And the significance, the reason I've written it that way, is if we have two vectors, u and v, and we're subtracting v from u, we start them in u and v in the same place, and then we draw the directed line segment from the vector's end that we're subtracting to the vector's end that we're subtracting from. So here's the v ending, and we're going to the u ending, and that's the way we would come up with u minus v. So that's a little exotic, and it's all because of all these other steps that we did to figure out that that's the way it will work each time. So we have to be a little careful. That's not particularly easy to do, and we have to work hard to remember how to do that. But again, I'll say it again. Let's go back up here. When we're adding vectors, and let me show you this. Sometimes we call this the parallelogram version, okay? If we would have had u and v have a common starting point, see, that would have been v right down here. We would have had u and v have a common starting point, which we can always do because those vectors can start anywhere as long as they have the right direction, the right magnitude. So think of the v being right down here. Well, then think of a parallelogram. That is, let's put a side that's parallel to this part and a side that's parallel to this part, and then the angle from the common, the vector from the common beginning to the opposite vertex of that parallelogram is u plus v. I prefer to think of it as the head to tail version like I've done here. Start with the vector we're adding to, and start the vector that we're adding to the u. It starts where u ends, and then our new vector goes from starting to very ending. Here we have to be a little more careful, and it's easier to do the subtraction, as I said. Put the vectors where they have a common beginning point, and start the u minus v. It starts where the vector we're subtracting ends and goes to the vector where we're subtracting from ends, u minus v. Well, that's a mouthful. It's easier if I could actually draw it in person. Let's practice this a little more on the next page and practice it mentally, obviously. In fact, here's what I suggest. We're going to do 3 problems, and remember, in these videos you can stop it, you can pause, that is, and you can try to do these by yourself before I actually show them. But we've got 3 vectors here, and v, u, and w, and I've got them drawn on this grid so that we can actually make sure that we do the right thing. So the first thing we want to do is illustrate, draw v minus w, and this is more than scalar multiplication. This is actually addition, subtraction, scalar multiplication all going together. So v minus w. Okay, well, what we need to do, remember, is we need to write down v. Okay, so here's our v, and then we need to take our w, what we're subtracting from, and potentially give it the same beginning place. And so what we would do is we'd go, notice how w goes. It's that we have 2 units horizontally to the right and 2 units vertically downward. So we could go 2 to the right and 2 downward, and then we could rewrite w over here. Well, let's see what, and then what would we do? We would connect the endpoints, but let's see how I've done this. Well, I did this, I guess, a little differently here. I'd forgotten that, okay? And maybe this is better for us at this point. Remember, v minus w could be thought of as v plus a negative w. So here's v. Now a negative w would start here and go to here. So we would go vertically to the left, horizontally to the left 2 units and vertically up 1 unit if we were starting here and going here. So that's what I've done. I've taken my vector v, which goes 3 horizontally and 2 up. 3 horizontally and 2 up. Now, minus w, or negative w, is what I'm adding, and it goes 2 left, 1, 2, and 2 up, 1, 2. And so if we started here and end here, then this is v minus w, and that means we start here and end here. Okay. Now, in the case, in this next example, we have 2v plus 3w. So we've actually got to scale v up by 2 units. So we've got to make it twice as long. And so that means we've got to go, let's think about that. We're going to have to go horizontally instead of 1, 2, 3. We're going to have to go horizontally 6. Well, let's look at what we've got. Let's just look at this. Okay. So we first have to decide what we're adding here. And our v, we're scaling by 2v. So we've got to make it twice as long, and to make it twice as long, we've got to make it go to the right twice as far and up twice as far. So it's got to go to the right 6 units. Well, let's look here. Here's where it starts: 1, 2, 3, 4, 5, 6. So yeah, it's going to the right 6 units, and it's got to go up twice as far. Here, its V is 2 units up, but we've got to have 2V, so it's got to be 4 units up. So how many units up? 1, 2, 3, 4. That's how we can draw 2V. Now we're going to add to that 3W. Okay, so we're going to start 3W here where 2V stops, and we've got to make W, 3W is 3 times as long as W. So that means it's going to go to the right 3 times further. Well, that'd be 6 units, and down 3 times further. That would be 6 units. So let's look. Let's figure out where we're going to find the end. 1, 2, 3, 4, 5, 6. It goes to the right, and 1, 2, 3, 4, 5, 6. It goes down. And so this is what 3W would look like. Okay, well then if we start here and go to 2V, there we go, and then we start from the end of 2V, we add 3W, then this is 2V to 3W. Now, this one's kind of convoluted because we actually have 3 different vectors involved, and the first thing that we've got is a 2V. So here's our 2V. It's twice as long as V. Okay, here's our 2V, twice as long. It means 6 to the right and 4 up. So here's the starting place: 1, 2, 3, 4, 5, 6 to the right and 4 up. 1, 2, 3, 4. So that's the 2V. Now minus W, here's W, minus W goes in the opposite direction, and so I put minus W right here. Now when we're finished with minus W, then we're adding U. So we start U at this endpoint, and we just put that U down here, which is 1 to the right and 3 up, isn't it? 1 to the right and 3 up. So after we put all those pieces together, then we go from the very beginning to the very end for our resultant vector. That is the result of adding and subtracting all of those vectors. Well, we're going to transition into the next discussion about vectors with the next slide. And there's 2 ideas to this. One is the component form of a vector, and the other is a position vector. Remember earlier I said that these vectors can lie anywhere in the plane as long as they have the right length, the magnitude, and the right direction. Then it doesn't really matter where they start and end, they'll still represent the same vector. So a lot of times we'll assume our vectors are called position vectors, and a position vector is a vector whose initial point is the origin. So if its initial point is the origin, then the end point will just be an XY pair in the plane. Okay, and so for instance, let's suppose that here's our vector V. Okay, let's ignore everything else except this vector V. So it begins at the origin, that's the initial point, and it ends at this point P. And let's assume this point P has the coordinates A and B. The X coordinate is A and the Y coordinate is B. Let's just make that assumption. Then we call the component form of this vector. You notice we put these little brackets here. Okay, we put these, these little looks like kind of a funny less than sign and funny greater than sign, and that's to indicate that it's not a point, it's a vector. And you can read all of this stuff here, but the most important information is this first position of this algebraic vector. Okay, this algebraic vector is the horizontal displacement the vector makes from its initial point to its terminal point. And the second component represents the vertical displacement from the initial point to the terminal point. And you notice on the previous pages, I was counting horizontally and counting vertically, and I was basically using this idea. How much are we moving horizontally and how much are we moving vertically? So if we see this vector named in this fashion, as in this component form, A comma B, that means we move horizontally A units from the initial point and B units vertically. And so initial to terminal, horizontal displacement, vertical displacement, and that's an easier way to think about these and deal with them later on. Now, this is where we're going to start in the next discussion, and that is dealing a lot more with the component form of vectors and how we add and subtract those.